Okay, so we've done horizontal launch. Now we're going to do angled launch. And we're only going to do level to level angled launch. We're not going to do anything where you jump off of a table and go up and then go down to the floor. We're only going to do things where you go off the ground and you land on the ground somewhere further away. We call those level to level angled launch. Okay, steps. There are 3 steps. First step, draw a picture and label it. Second step, make a chart and fill in knowns. Third step typically is going to be solve for t, and you can use the y or half y data for that. Okay, so what does your picture look like? There's your picture. It's an arc. Okay, it looks like an arc, like a half circle kind of thing. You have an angle theta right there. And you'll have an up angle and a side angle. The up angle is your V initial y. The one going to the side is your V initial x. The one going at an angle is your V initial. The height is s in the half y. That's an s, and that's a subscript of 1/2 and y. S in the half y is your height. Your range is s in the x. We typically ask you for time, height, and range on each of these questions. The first thing you do is solve for time. After that, you can solve for anything else. Now, if we zoom in on just what's going on here, okay? If I move that little angle over here, right? Here's my angle theta. This is my VIX, the up one is my VIY, and the hypotenuse is my VI. So once you've labeled your picture, just so you know, there's 2 equations and you are expected to memorize them. They're not on your formula sheet. Your VIX is equal to VI cosine theta. Your VIY is equal to VI sine theta. Okay, so once you've got your picture, and I'm telling you where this is coming from because I'm going to put it in a chart. So then you draw your chart. Your chart will have an X, a Y, and a half Y. I'm drawing it kind of big so you can see everything. You could draw it smaller. And you're going to do the VI, VF, AST down the vertical. Your VI and your VF and the X are constant velocity. You have to remember that your X stuff, your X direction stuff is still constant velocity. So that's Nolan Ryan pitches a ball. It leaves his shoulder as fast as it hits the the catcher's glove. It's going the same speed in the horizontal, okay? So your VIX is VI cosine theta. So this is VI cosine theta. I don't want you to write that in the box. When I give you these problems, I expect you to stick that in your calculator and write the answer that comes out of your calculator in the box. And I'll show you an example in just a minute. But your VI and your VF and the X are going to be the same. So that's also VI cosine theta. You're not accelerating in the x, so your a in the x is 0. Your s in the x will be your range. Your t is, I'm just going to call it t for right now. Okay, now in the y, it's exactly as if you threw something up and it came back down and you caught it. That's all you're doing. You throw it up and you catch. That's all that's happening in the y. It goes up, it comes back down to the exact same point. Okay, so my initial velocity in the y is my VIY. So that's VI sine theta. It's going up, so it's a positive number. When it comes down, what's different about it? It's negative. So you have negative VI sine theta. What's your acceleration? It's in the y. Negative 9.81. Good. Okay. The s, if it goes up and it comes back down to the exact same point, what is your s? 0. If it comes right back to the same origin that it started from, it has not gone anywhere. Its displacement, its net displacement is 0. The time that goes up and back down and the time it goes across are exactly the same time. The s and the half y, so when I do the half y math, I'm going to talk about just the part where it goes up and gets to this point. So when it goes up and comes to the middle, where the height is, the height of the point. Okay? That's all you're doing for the half y stuff. So for the half y, your v initial is the same as it is in the y, so it's VI sine theta. But at the top of any arc, for a split second, it stops before it changes direction to come back down. So your v final is 0. Your acceleration the entire time, whether it's at the bottom, the top, on its way back down, halfway through, it is always negative 9.81. Gravity doesn't change unless you jump off the planet and go to another planet. It is still negative 9.81. No matter where in the trajectory you are, acceleration due to gravity is 9.81 meters per second squared. The s, the displacement that it goes for that halfway point, that will be your height. And this will take half of the time it took to go x or y. So this is half t. The half y will give you half the time, but it will give you the total height, the max height. Okay? Now, what equations do we like to use with this? Okay. So, well, the x portion is going, it's at constant velocity. So if you're thinking about like your range, okay, s equals VIT plus AT squared over 2, right? What's your acceleration in the x? It's 0. So that means this whole portion goes away. So s in the x is equal to VIX times time. And that will give you your range. Okay, for your height, you're going to use your half y data. And your half y, s equals VIT plus AT squared over 2. Well, nothing 0 except v final, and nothing like that's not in the equation. So this is the equation you're going to use to find height. To find time, sorry, you can use the y or your half y. Just remember, though, that half y is half the time, and y data will give you the whole time. But I would just use the acceleration formula where you flip the a and the t. So then t equals v final minus v initial over a. That will give you, okay, well, I'm not really good at drawing lines today. That will give you your time. V final minus v initial over a. You can barely see that. Okay, so here's an example problem. The cannon is fired. It fires around at 20 meters per second at a 35-degree angle, and I want to know the time, max height, and the range. So first, I'm gonna draw a miniature picture. I'm not gonna draw a big picture. So here's my miniature picture. My angle is 35 degrees. My VI is 120 meters per second. I'm looking for height. I'm looking for range. And I'm looking for time. So I'm looking for 3 things, and yes, I drew it microscopic. It's just a tiny picture. Okay. So then I need my chart. Okay. Oh, okay, so my VI is 120, my theta is 35 degrees. First of all, let's check our calculators and make sure that they're in degree mode. Make sure your calculator's in degree mode, because this won't work if it's not in degree mode. Okay, so I want VI cosine theta for my VIX and VFX. So 120 cosine 35, and I get 98.3. It's close enough, right? So 98.3, 98.3 for my VIX and my VFX. Now for the Y, I need 120 sine 35. So you're just pressing buttons in the calculator. So you get 68.8. So my VIY is 68.8. My VFY would be negative 68.8. My VI in the half Y would be 68.8. My VF in the half Y is 0, because that's at the top point of the trajectory. My acceleration in the X is 0. In the Y, it's negative 9.81, and in the half Y as well. And I'm looking for range. Oh, and S in the Y is 0. I'm looking for range, height, and I'm looking for time. So those are the things that I am missing. Okay, so to find time, you can either use your Y or your half Y. I'm going to go ahead and use my Y values. So I'm going to use Y to find time. Time is V final minus V initial over A. So I'm going to use my Y data. That's why I put a Y there, because I'm saying I'm not even going to look at these two parts of the chart. I'm only looking at the middle part with the Y, okay? Okay, so then that's negative 68.8. I would put the top in parentheses also. Minus 68.8 over negative 9.81. And so my time is whatever that is. So I get 14.0 seconds. So there's my time. I solved part A. Okay. So I'm going to put that in my chart. So my time in the X is 14.0 seconds because it's the same as the time in my Y. But my time in my half Y is going to be half of that time. So it'd be 7 seconds, yep. Okay, why? Because t in the half y is 14.0 over 2, which is 7.0 seconds. I wanted the total time, though. I said, how long is it in the air? That's the total time, okay? All right, so then part B says, what is the max height? So for part B, I'm going to use the half y data. So if I want height, that's S. and that equals VIT plus AT squared over 2. So then S equals, I'm looking at just the half Y, just this part of the chart. Do not cross-contaminate. So VI is 68.8 times 7.0 plus negative 9.81 times 7.0 squared over 2. And then you just stick it in your calculator. You see that? No. So I get 241.3 meters. And that is my max height. So that's how high the shell goes. So then the last thing that I need to know is the range. So for part C, you can't see that. See. I'm going to use my X data for the range. S in the X is equal to VIX times time. And you could tack on, if you wanted to, plus AT squared over 2. But just remember that the acceleration in the X is 0, which means that AT squared over 2 is also 0. So then you just have to plug in what you have. Your VI in the X, and again, if I'm doing X data, then I'm only looking at the X part of my chart. I'm not looking at the Y or the half Y, just the X part. So then that would be 98.3 times 14.0. So 1376.2 meters. I can't. Here we go. And that is a typical angled launch problem.